Rationally Speaking is a presentation of New York City skeptics, dedicated to promoting critical thinking, skeptical inquiry, and science education. For more information, please visit us at nycskeptics.org.
Welcome to Rationally Speaking, the podcast where we explore the borderlands between reason and nonsense. I am your host, Massimo and with me, as always, is my co-host, Julia Galev. Julia, what are we going to talk about today?
Massimo, this is the second of two episodes that we're taping with Graham Priest, who is the Boyce Gibson Professor of Philosophy at the University of Melbourne and a Distinguished Professor of Philosophy at CUNY Graduate Center in New York. Our last episode with Graham, you may remember, was about Eastern philosophy, and this time we're going to talk to him about another specialty of his, which is paraconsistent logic. So Graham will delve into this in a minute, but just to offer a teaser, it may seem like incredibly self-evident, like one of the most self-evident truths there could possibly be, that something can't be simultaneously true and false. Well, that is a self-evident truth we are going to call into question today.
Okay.
So, Graham, could you give our listeners just a brief definition of what paraconsistent logic is?
Okay. If you go to a university and you take a first course in logic, you will almost certainly be taught that once you have a contradiction, everything follows from that.
A contradiction being?
Well, let me give you an example.
Great.
You will be taught that if you suppose that the sun is and is not made of green cheese, it follows that I'm a frog.
Clearly.
Obviously, right.
Okay.
And why is that?
Okay, let's not go into too technical details.
Okay, yes,
for the
I'm
moment.
sorry. I did ask for a quick...
We're only 30 seconds into the podcast, yes.
Okay, withdrawn. Go on, please.
Okay, that does seem kind of crazy. Okay? Because the moon being or not being made of green cheese would seem to have nothing much to do with you or frogs. Okay.
It would seem. It would seem.
It would seem.
Yeah.
But this illustrates the fact that in the logic education that you're likely to receive, you will be taught that if you've got an inconsistency of the kind that I gave you, then absolutely everything follows. That you're a frog, you're not a frog, that the moon is purple, that Socrates was Chinese, that I'm on the moon, you know.
An explosion of nonsense, basically.
Yes.
Or non sequiturs.
So this principle of inference is often nowadays called explosion.
Aha.
Because the inconsistency explodes.
Right.
Now, that principle of inference, explosion, is a relatively recent piece of logical technology. You don't find it in ancient Greek logic. It's debated in medieval logic. It doesn't really become orthodox in logic until about the turn of the beginning of the 20th century.
And is it the case that explosion is important because it shows you why you can't have contradictions?
Many people will say that explosion shows you that you can't have a contradiction, because if you did, then everything would follow, and that's crazy.
It's weird because it seems to me like the reason you can't have a contradiction is just because it doesn't make sense. It almost seems like you don't need an explanation for why it doesn't make sense to contradict yourself.
Okay, that's a very traditional view. I mean, that was Aristotle's view, I think. So let's come back to that in a second. I mean, your original question was, what is a paraconsistent
Yes, I'm
logic?
sorry. I'm sorry. Please
now,
go on.
I want to explain what an explosive logic is. It's one where these contradictions explode. A paraconsistent logic is exactly one where explosion is not valid. So you can have a contradiction. Some things may follow from it, but it's not the case that everything follows. So if you're dealing with this kind of logic, you can treat contradictions as kind of singularities. They're kind of isolated, so they don't sort of ruin things in a way that explosion will ruin something, a theory that's inconsistent.
It's a way to contain the logical explosion, basically.
It's a way to contain contradictions and make sure they don't sort of infect other things. So you can contain the contradiction that the moon isn't made of green cheese, and it won't affect anything about you being a frog, for example.
Will it affect anything else besides?
Yes, it can do. It depends on interconnections. So one reason why people are interested nowadays in inconsistent theories is because of certain paradoxes that arise in theories of sets of truth and so on. If you have general principles of sets, then contradictions about some sets will have other implications for some sets. So there can be consequences, but they're controlled consequences. They're not this kind of lunacy about everything following.
What would be an example of a paradox that paraconsistent logic was intended to deal with?
Before I answer that question, let me say something about dialethism. Dialethism is the view that some contradictions are true. Okay? So it's not a view about logic, it's a view about semantics or metaphysics. But obviously there's a connection. Because if you think that some contradictions are true, and you don't think that everything is true, then you must subscribe to a paraconsistent logic. Because you've got this true contradiction, and you don't want to explode in front of you. All right.
Maybe this is just my traditional self-talking, but when you say some contradictions are true, I want to ask, well, which part of the contradiction is true? Not all of it can be true. It's a contradiction.
Both parts. Okay.
No.
We'll come back to this in a minute, but let me just finish drawing this distinction.
Okay.
Because you did ask me what sorts of examples there were, and
yes.
I'll answer that. So if you hold this metaphysical view, dialethism, you'd better subscribe to a paraconsistent logic. But there are lots of people who work on paraconsistent logic who are not dialethists because they just think that explosion is crazy. So, for example, paraconsistent logic has applications in information processing where data can be corrupt and contradictory, and you don't want your data to explode. Or if you look at the history of science, it's pretty clear that there are actually explicitly inconsistent theories, such as the early calculus, such as Bohr's theory of the atom. And these guys reasoned in a sensible fashion. Now, I'm not suggesting that these theories were examples of dialetheas. I mean, Bohr's theory was never, accepted as literally true. But nonetheless, these guys had to use a paraconsistent logic, whatever it was, in drawing their conclusions. Okay, so...
because at that moment, let me see if I understand this correctly. For instance, in the case of Bohr, I looked into that when I read your article in the Stanford Encyclopedia of Philosophy, which does mention that example. So you're saying that they had to be used, Bohr, for instance, had to be using a paraconsistent logic, whatever that was, because he was not resolving, he was using a theory that later turned out to be incorrect or rejected or whatever, but at the moment he was using it to derive partially valid inferences, and yet somehow part of the theory's construct were in fact contradictory,
yes,
right?
Yes, I mean, he was deploying the quantum principle, which says energy is discrete, and he was using classical mechanics in which it's continuous. And he was making lots of interesting predictions about, the spectrum of the hydrogen atom and so on, which turned out to be right. Okay, the theory turned out to be wrong in the end, but I mean, Bohr was well aware that he was, using an inconsistent theory. He wasn't very explicit about what was allowing him to draw inferences, but it must have been. I mean, obviously, he didn't, conclude that the spectrum of the hydrogen atom has 3,476 lines, which would have followed given explosion. So, I mean, he must have been deploying some kind of paraconsistent logic. So that's just to say that many people would think that paraconsistent logic is correct without being dialethists. Okay, well, I'm a dialethist. Okay, so that's all ground clearing for your question. So what kinds of things, what kinds of contradictions might be true? Well, several different things have been suggested, but I think probably most people's favourites are certain paradoxes. So they're paradoxes of self-reference. Some of them are very old. So probably the oldest and most famous is something called the liar paradox. I'll tell you what that is in a moment. And that was discovered about the 3rd, 4th century BCE in Greece. And some of these paradoxes are relatively recent. They turned up in a very unexpected place at the end of the 19th century in the foundations of mathematics. So one's immediate reaction to these things might be to write them off as a kind of party game, but you can't do that now just because of the central role that these things have played in the foundations of mathematics in the 20th century. Okay, so what sort of paradoxes am I talking about? Well, the easiest one to get your head around is the liar paradox. Mm-hmm. So, suppose I say that these very words that I'm now uttering are false. Is what I say true or false? Well, suppose they're true. Mm-hmm. Well, but what did I say? I said these very words I'm uttering are false. And if that's true, well, they're false. So if it's true, it's false.
Right.
Okay. Mm-hmm. So suppose it's false. Well, what did I say? I said these very words are false. And if they are false, well, like me, they're true. So they seem to be both true and false, whichever way you go.
Can't they be neither true nor false? Can't they be nonsense? Just like it's neither true nor false that the Gostak distims the Doshes because the sentence is nonsense. It's, well, I use made-up words, but I could make a nonsense sentence with English words too.
But the thing is, sorry, before Graham answers that question, there's a difference between literal nonsense, like you can make up words or whatever, and what Graham just said. I can understand what he said. I can attach a meaning to what he said.
So maybe it's just a different kind of nonsense.
Well, that may be, but what I'm saying is there's a difference there because right, I can understand semantically what he's saying, and it's the problem is that when I try to make sense of the logical consistency of what he's saying, then I run into the paradox. But prima facie, it's at first glance that I understand perfectly well what he's saying.
Yeah, look, you can say the words are meaningless. You can say they're neither true nor false. These are not the same thing.
Right.
And I think for the reasons that Massimo gave, the view that these words are meaningless isn't very plausible because they're grammatical and you understood well enough to follow the reasoning and so on. The suggestion that they're neither true nor false, I think, has more legs. And indeed, this is one of the standard views about these paradoxes. There are problems with it. Let me explain one. Okay, we're going to have to do a little bit of reasoning here, so we'll take this slowly.
Okay.
Okay, the paradox I gave you before was the liar paradox, and the words were, what I'm now saying is false. Mm-hmm. Okay. And let's consider the possibility that those words are neither true nor false. And that'll do it for you, okay? Because what we saw was if it's true, it's false. If it's false, it's true. Okay, so maybe neither, problem solved. Okay. But now I want you to consider something else. I'm going to say something else, which is this. What I'm now saying is either false or neither true nor false. So I've taken your suggestion on board, right? Mm-hmm. And what I'm now saying is either false or neither true nor false. Okay, what's the status of these words? Well, if they're true, then they're either false or neither true nor false, and that's a contradiction. If they're false, then they're certainly either false or neither true nor false.
So the total sentence is true.
So it's true. Okay, and now if you want to say, hey, Graham, these things are neither true nor false, then I say to you, well, Julia, if they're neither true nor false, well, then they're certainly either false or neither true nor false. And so,
that's
hey,
clever.
they're
That's
true
clever.
again.
I like that.
This is a phenomenon which logicians tend to call revenge.
What's it called?
Revenge.
Revenge.
The revenge of the liar.
That's great.
And it's a very common phenomenon in discussing paradoxes of this kind. Mm-hmm. Whenever a theorist comes along with a sort of putative solution, you can actually take the concepts that they deploy and you can kind of give an extended paradox or a revised paradox or a revenge paradox. The thing that these paradoxes all depend on self-reference, and self-reference allows you to kind of take any division and twist it and destroy it and break it. So self-reference is kind of a construction which can be used to tear boundaries. And, any solution is going to put up boundaries, and then you deploy self-reference to tear them down. So, this is part of the argument why consistent solutions to the paradox of this kind ain't going to work, because you've got machinery to tear through boundaries. And the dialectic approach says, hey, these things are both true and false. This is a very strange creature which actually crosses boundaries, or sort of permeates between boundaries, the boundary between true and false, or whichever boundary you want to draw.
So when I suggested that maybe we should say the sentence is meaningless, what I sort of meant by that was that maybe we should declare the concept of self-reference to not make sense. You just can't refer to.
But you can't do that, right?
A sentence can't refer to itself.
But it actually does. But the concept of self-reference does do quite a bit of work in mathematics and logic and a bunch of it, right? So you really can't get rid of it. Yeah. Although I'm glad that you actually stated what I was about to ask you, which is, it seems to me that a lot of these paradoxes, if not all of them, that do deal with self-reference. So does that is it reasonable for you to say, for instance, for somebody to say that, okay, look, then what we can do is to deploy, let's say, classical logic in any case other than cases where there is self-reference, and then when there is self-reference, we use something else. What I'm getting at here is that logic, after all, one way to look at logic, at least, is as a set of tools that have a proper domain of application, just like every tool. And so you run into an issue where that tool doesn't work, and instead of trying to use a screwdriver to hammer something into a nail, you say, well, I need a hammer now, I need something else. Does that is something like that available to the logician?
Well, the quick answer is yes.
Okay.
The slow answer is that it depends. The details depend on how you conceptualize logic. There are certain people who think that there's no such thing as the one true logic, that logic is a tool, very much like you described, and you can help yourself to any bit which gives you the right result. So you're kind of an instrumentalist about logic, and that's possible. There are some people who think, no, there's one true logic. You can't be a pluralist. If you subscribe to that view, then you certainly can't run the line I've just described, but you can do something very similar. So if you look at the way that logic works, then logic deals with reasoning about a whole bunch of cases. Okay, and sometimes you will find yourself in a special case, in which case you can use the special case of... you can consider the general logic, which is restricted to that special case. And then that might be... that might give you the effect of using a different logic, although you haven't changed your logic, you're just considering the application to a special case. So in either of those ways, if you are reasoning about a situation which is not dialectic, then you're in this kind of special case, and you can use standard logic, or first year logic, which has explosion. But if you are in a situation which throws up these dialethias, well, then you can't do that. You have to use the full strength paraconsistent logic.
So, I'm sorry, go on. Are there different kinds of paraconsistent logics?
Yes,
and if so, which one do you subscribe to? Or what are some distinctive features of the one that you subscribe to?
Right. Paraconsistent logic is not one thing. There are many, many. I mean, there's interesting history here. I mean, the modern paraconsistent logics were constructed for the first time in the 1960s, 1970s, and they were constructed in many different countries by people who are unaware of what people in the other countries were doing. So they were constructed in...
That was before the internet, I suppose.
Yes. So they were constructed in Brazil, in Poland, in Canada, in Australia, and often these logics are constructed on very different assumptions. And it may well be that if you're using logic instrumentally, you would choose different kinds of logics, different kinds of paraconsistent logics. But generally speaking, the sort of paraconsistent logic that I favour for discussions of things like the liar paradox is one kind of paraconsistent logic called a relevant logic, which was actually invented by a couple of American logicians, Anderson and Belknap, in the 1960s. Mm-hmm. And what Anderson and Belknap insisted was that if you've got an inference, then the premises really must be relevant to conclusion. It sounds kind of strange, right? But it's a very obvious thought. But if you enforce this, it's obviously going to rule out things like explosion, because in an instance of explosion, the contradiction is obviously relevant to an arbitrary conclusion. So,
is there any more formal way to define what's relevant, or?
Yes, there is.
Okay.
I'm not sure we want to go into that. Okay, well, I'll leave it to you.
Well, okay. Look, to do it properly, you need to go into the technical details, and I think probably that's not an appropriate thing for this occasion.
Okay.
But I do want to follow up on what you and Julia were discussing a minute ago about. Let me go back to this idea of logic as either universal or instrumentalist. These two views of logic. So one of the shocking or sort of revealing turning point in my academic career was when I went back from being a originally a biologist, went back to graduate school and started taking courses in philosophy. And one of the courses, the title of one of the courses in the book that came with it was Logics, plural. And I looked at it and I said, well, there's might be something strange here. Could it be that they made a mistake and misspelling on the cover of the book? And no, as it turns out, it wasn't. I was introduced to this idea that there are different kinds of logics that can be deployed, have different domains of application and different properties. Now, that said, however, could it be that there is a reasonable position that let's say I could define, for lack of better terms, as a quasi-instrumentalist, because in this sense. Yes, different logics have different domains of application, different properties. And in fact, your own example of people developing different kinds of paraconsistent logic starting from different axioms, different assumptions, fits the bill. But it's not that you can do that arbitrarily so. It's not that you can just invent whatever the heck you want and make sense of it. In a similar sense, it seems to me, to, let's say, mathematics. You can have, or geometry, right? You can have a Euclidean geometry and non-Euclidean geometry. They do start from different set of assumptions. They have different consequences and properties and different domains of application. But it's not that you can say, therefore, anything goes, and I can just invent my own kind of geometry and it's going to do any arbitrary work, right? So in that sense, one could still salvage this idea that logic is non-arbitrary, and therefore, in some sense, universal, like math would be universal. But that doesn't mean that it's not pluralistic. Right?
That's quite a coherent view. If you think that the kind of
Julia, please score this under my rubric because I just been told by a logician that I had a coherent view. Thank you. Go ahead.
Well, but if you had an incoherent view, that'd be fine, right?
Yes, of course.
We'll just deploy paraconsistent logic. And
hang on. You shouldn't identify contradiction with incoherence.
Right.
Explosion turns a contradictory situation into an incoherent one.
Good point. Yes.
Okay.
Interesting. Yeah.
Which reminds me, we're going to come back and talk about why you might think that contradictions can't possibly be true. But let's deal with Massimo's question first. So suppose you hold the view that different domains of inquiry or different topics require different logics. You may well hold the view that the domain or the topic nonetheless requires the particular right logic for that domain or topic. Mm-hmm. Okay?
Right.
And that's some kind of pluralism. And, there are some paraconsistent logicians who hold that view. I think Newton da Costa, one of the first paraconsistent logicians who invented a number of paraconsistent systems in Brazil, that this was his view, I think. Or this is his view. He's still alive. But I think one needs to be careful here because there's an important distinction that often gets slid over in discussion of logical pluralism. in one sense, logical pluralism is obviously true. There are many different logics, like there are many different geometries.
Right.
Okay, there's classical logic. That's the logic of Frege and Russell. Invented 100 years ago. There's Aristotelian logic, there's paraconsistent logic, there's intuitionistic logic. There's obviously a plurality of these things. But then, of course, there's a plurality of physics as well. There's Newtonian physics, there's quantum physics, there's Aristotelian physics. The fact there's a plurality of theories doesn't tell you that there isn't one right one.
Right.
Okay. Similarly, the fact that there's this plurality of logics doesn't tell you that there isn't one right one.
Right.
So,
in fact, if I may help you on this one, for the benefit of our listeners, the example with Newtonian mechanics is particularly interesting because, of course, the first reaction that could be, well, yes, but we know that Newtonian mechanics is wrong, and so let's say relativity is right. Yeah, well, maybe, except that we do use Newtonian mechanics for all sorts of actual practical purposes, including sending space probes around. So it is actually useful, even though we know that it's not technically correct.
Absolutely. And this brings us back to our discussion of whether you can use different logics without sort of jettisoning the view there's one true logic.
Right.
Because Newtonian mechanics is a sort of special case, a restricted case of relativity. Not exactly, but, for low velocities, they're practically the same.
Right.
Okay. So you can use Newtonian mechanics because you're dealing with a special case of low velocity. In a similar way, you might subscribe to a paraconsistent logic, but then in the special case where you're not dealing with these inconsistencies, you can use classical logic because it's practically the same.
It seems to me, at least, like it would also be plausible that there wouldn't be maybe one true logic, but that you still have to just pick one. Like you can pick any one you want, but then you have to stick to that. That seems like another plausible view.
Would you say the same is true in physics?
No.
Why not?
Because logic is like a creation that it's something that we've created, and the form that it takes depends on like the starting axioms or how we want to define it, and that's not true of physics.
Well, yes, it is. I mean, Newtonian.
Well, it's true of theory. Sorry,
correct.
It's not true of how the world works.
Right now,
it's true. Yeah.
So, both physics and logic, you can have theories. Okay. Now, why? I mean, if you're a realist in physics, you suppose that all these different theories can't all be true. One must be right. Now, why should you suppose that logic's any different? You've got lots of theories.
Well, what would you hold the theory up against to see how well it does, the way we do with scientific theories?
The facts.
Logical facts, mathematical facts,
Logical
physical
facts.
facts. Yes, right.
But
Right.
don't the very question of what are logical facts seems to depend on what logic you choose. So
No, that's
No?
not true.
Okay, so help
Let
me
me give you an
understand that.
analogy. Consider grammar. I mean, technical grammar, in the sense of, Chomsky's grammar or something like this.
okay.
When you've got a language such as English, you can construct different grammars. Some of them are right. Mostly they're wrong.
Mm-hmm.
But one aim of linguistics is to get a grammatical account of something like English. How do you know when the grammar is right? Well, you compare it with the facts.
Mm-hmm.
What facts? Well, the facts about what people who speak the language will tell you is grammatical and not.
So what?
Even though,
I understand that example,
even
but
though
then how do I?
language is in fact a human creation,
Correct.
obviously, right? So that's the analogy. So
Well,
even if you think of logic or mathematics as human creations, which, by the way, in some sense they obviously are. In some sense, we could have a whole different discussion there about things like, I don't know, mathematical Platonism, for instance. But even without getting there, I think the analogy with language is apt. The language is clearly human creation, and yet there are such things as linguistic facts that you can use to test your theories.
Well, unless I'm misunderstanding the analogy, it seems like the logical fact then would, if you ask me, I would tell you it is a logical fact that something can't be both true and false at the same time. But So how can you tell me
But
that
the structure
that's
of a
wrong?
paradox does actually make clear that that is the case. I mean, the liar's paradox, when you analyze it, does show that, well, as it turns out, as a matter of logical fact, that something can be true and not true at the same time.
Well, no. That seems like a strategy we might use to deal with this paradox, but not a strategy that is uncontroversial.
Okay, let me make a minor correction.
Okay.
That no contradictions are true is not so much a principle of logic, it's a principle of metaphysics. Okay? Principles of logic tend to be what follows from what.
Mm-hmm.
Okay? Mm-hmm. So, does an arbitrary conclusion follow from a contradiction? I mean, that's certainly a fact of logic. And when you construct a logical theory, you can test it against the facts of logic, the things that we know. Does this follow or does it not? And we have intuitions about that, just as we have intuitions about, whether a sentence of English is grammatical. But let's come back to this question you asked right at the start about why you should suppose that contradictions can't be true. Bit of background here. Generally speaking, that's been high orthodoxy in Western philosophy, not so much in Eastern philosophy. But there's only been one substantial defence of it in the history of Western philosophy, and that was by Aristotle, and it was in the Metaphysics, not the logical texts, the metaphysical texts, right? Mm-hmm. And Aristotle had a bunch of arguments that have nothing to do with explosion, but his defence of the law of non-contradiction has been very, very influential because no one really has felt the need to defend the law again until recently, when it's been put under pressure by people like me. All right, so you might think that Aristotle's reasoning was very cogent. Well, it's not. I mean, I won't go into the details here, but there's one long argument which is so tortured that experts can't even agree on what it is. They can't even agree how it's supposed to work, let alone that it works. And then there's 6 or 7 small arguments, most of which are clearly beside the point. And that's obvious. So, why has Aristotle's influence been so persuasive? Well, that's a really good, sociological question. Nearly everything else that Aristotle said has been refuted or at least seriously challenged. It's taken 2,500 years to get round to the law of non-contradiction.
But has that been persuasive? Because my assumption would have been a priori that it just is so self-evident to people that you can't have something be true and false at the same time that they wouldn't have needed Aristotle to convince them of that.
I think that the psychological answer there might be that it's so strongly intuitive. But of course, the fact that it's something strongly intuitive doesn't mean that it's true. I mean, it took us 1,500 years to question the idea that the Earth is flat. So.
Yeah, and not only that, when Galileo suggested the Earth moves, people took it to be obvious that he was wrong. Mm-hmm. Because after all, we do feel the Earth move sometimes, in earthquakes. And we know it's not like that. So it seemed obvious to people. So I mean, this seems obvious to you. But, let me ask you, why do you think that's true?
Why do I think it's true that something can't be true and false at the same time?
Yeah.
Because that seems built into the definitions of true and false to me.
The definition of true is what?
I'm not going to answer that because I can't. But if you, I guess I should just say that if someone were to talk about something being both true and false at the same time, I would no longer know what they meant by the words true and false.
Really?
Yes.
Did you not understand when we were talking about the liar paradox?
Yeah, I understood
so you
that.
would understand.
Well, but there are some things that No, I wouldn't understand if something was true and false at the same time.
But we just went through an example where you did.
No, sorry. I meant I understood what was meant to be communicated by the liar's paradox. I wouldn't understand what would be meant to be communicated by saying that the statement is both true and false at the same time.
Mm-hmm. Let me give you an example from the history of mathematics.
Mm-hmm.
For most of the history of mathematics, people have thought that actual infinitudes are incoherent because they seem to be embroiled in a bunch of paradoxes. For example, that if you take the whole numbers, 0, 1, 2, 3, 4, 5, and you take the even numbers, 0, 2, 4, 6, 8, you compare them off 1 to 1. So there seem to be exactly the same number of numbers and even numbers. And that's crazy, because the even numbers are missing half of them, right? So this was an argument that has been known from a long, long time by the Greeks. And people supposed that showed that the whole notion of infinitude was incoherent. Now, things changed radically with the work of the German-Danish logician Georg Cantor in the 19th century. And Cantor said, no, what you've got to understand is that this fact that you can throw things away from a set and have the same number of things, this is not incoherent. This is actually the definition of infinitude. The difference between a finite set and an infinite set is that with a finite set, if you throw things away, the set gets smaller. With an infinite set, if you throw things away, the set can remain the same size. And the reason you haven't got your head around this, guys, is because you've only been thinking of the finite. Because, you've never taken the infinite seriously. But now I'm going to do this. Okay, so what Cantor was pointing out was that these sort of things which were paradoxical could actually be true, and that they seem false just because of it's what Wittgenstein called an inadequate diet of examples.
Now, that our intuitions are trained on
correct.
A set of things that don't include that.
So what I might suggest to you is that your intuitions about not about contradiction and non-contradiction are coming from this inadequate diet of example, because you've only ever thought really about consistent situations. Hey, but I'm giving you, some inconsistent situations, and you can see that, maybe they're like sort of the paradox of the infinite. We just need to, chill out and think about more unusual situations. There's more in heaven and earth, Julia, than is dreamt of in your philosophy.
Don't know.
Now, I can't let this episode finish without mentioning something that you actually do take briefly up in the SEP article, the Stanford Encyclopedia article, and that's Gödel's theorem. A lot of our listeners probably have heard of Gödel theorems. Actually, there's more than one, incompleteness theorems, and I've seen an inordinate amount of misuse of those theorems.
Indeed. So have I.
But the reason I'm bringing it up is perhaps, for one thing, to ask you very briefly to actually explain what the theorem actually says that it's relevant, might be relevant to this audience, but largely because you say that a paraconsistent approach to arithmetics overcomes the limitations of arithmetic that are supposed to, by many, to follow from Gödel's theorems. So from what I understand, you're suggesting the paraconsistent logic can actually be a way to sort of overcome and get around the limitations imposed on arithmetics by Gödel's theorem. Would Bertrand Russell be happy about this?
No, because he subscribed to explosion.
Okay.
Okay, let me try and take this as simply as I can.
Maybe we should start with the theorems theorem.
Indeed. So, Gödel's theorems are about formal theories of mathematics, like set theory or arithmetic and so on. And what Gödel showed, well, let me state it as it's normally stated, but in very loose terms. What Gödel actually showed was that provided you've got a mathematical theory which is sufficiently expressive, which you obviously want in a mathematical theory.
So non-trivial, not a trivial small little thing.
Well, it's got to contain certain mathematical machinery. Okay. And that's technical in nature, but I'm not going to go into that.
Yep.
But if you have got a theory of this kind, then there are going to be things which are true of the topic matter which you cannot prove in the theory. Okay. So the theory is specified by a set of axioms. And what Gödel showed, according to the traditional story, is that the axioms are always going to be incomplete, in the sense that for any axiomatic system you construct, there are going to be true things which cannot be proved. Okay, so
from within that system.
Right. Now, actually, what Gödel showed was not quite that. what he showed was that if you've got a mathematical theory of the appropriately strong kind, it must be either incomplete or inconsistent. Okay, that's what his result actually shows. Now, of course, Gödel didn't know anything about paraconsistent logic, and most people who write on Gödel's theorems know nothing about paraconsistent logic.
And so they ignored the inconsistency
Well,
part.
so they just didn't take the other possibility seriously.
Right.
Now, one thing that paraconsistent...
We're learning in this episode that it's all about taking things seriously, apparently.
Well,
there's a lot of that been going on the last few minutes, yes.
Yeah, I mean, one thing that paraconsistent logic does is open your eyes to all kinds of possibilities which were closed off to you before. Anyway, so coming back to Gödel's theorem, paraconsistent logic does not challenge Gödel's results in that form, that it's the theory is either inconsistent or incomplete, but it gives you the paraconsistent logic gives you the opportunity to explore the other possibility,
right.
Namely that the mathematical theory is complete but inconsistent.
Right.
And we now know that there are mathematical theories of this kind where you can prove everything that's true, including some contradictions. Okay. But they're inconsistent.
And for listeners, Graham was pointing to Julian. That's
Yes.
why when he said that.
Raising his eyebrows, that's true.
Okay, so that's sort of one way of looking at what I meant when I was explaining the relevance of paraconsistency to Gödel's theorems.
All right, well, that was an impressively concise and clear explanation of incompleteness and Gödel. I didn't expect you to be able to do that in 3 minutes, so well done. We are now out of time, so let's wrap this up and move on to the Rationally Speaking picks.
Welcome back. Every episode we pick a suggestion for our listeners that has tickled our rational fancy. This time we ask again, for the second time in recent memory, our guest Graham Priest for his suggestion. Graham?
Okay, can I be greedy and have two?
Sure.
Okay, they're very, very, very different. One of my favourite pieces of philosophical writing is Hume's Dialogues on Natural Religion.
Oh, we have something in common there.
Okay, it's a fabulous piece of writing. It's beautifully crafted as a piece of writing. It's philosophically engaging and cogent, and it's done that in such a way that anybody can understand this. It's not hard technical philosophy. Hume writes in a very engaging fashion, and many of the arguments that you hear people put up nowadays for the existence of God were pretty conclusively destroyed by Hume in the 18th century. So I think if you want to talk about the philosophy of Christian religion, you need to read Hume's Dialogues. And it's such a beautiful piece of writing. I'd recommend that to anybody who's interested in the existence of God.
And your second pick?
Okay, the second one, I'm going to be self-serving, because what we've been talking about is logic, and logic can get very technical very fast. But it engages with a number of philosophical questions, like some of them we've been discussing now. But the engagement of logic and philosophy is manifold. And I've always been interested in technical logic when I am because of its philosophical engagement. So some logicians are interested in proving theorems, and I do that stuff too. But for me, if it doesn't engage with philosophy, it's like playing chess. It's fun, but that's it. So I think that philosophy and logic should be taught hand in hand. And a number of years ago, I wrote a book called Logic, A Very Short Introduction. So Oxford University Press does this whole series of books called Very Short Introduction. It's a really nice series. They're sort of meant for the kind of the non-specialists in these areas. Okay, and I've read several of these books, and they're always done really well. Well, with the possible exception of mine. Okay, but anyway, I wrote the book on logic in the Very Short Introduction, and what it does is explain to people the basics of modern logic, by talking about the way that these ideas engage with various philosophical problems, such as the existence of God, or the nature of time, or gosh, I've forgotten what other things are in the book. Non-existence and impossible objects. I would recommend that to anybody who'd like to understand why logic is important if you want to think about some issues in philosophy.
I will second that. I actually read the book. So
Excellent. I haven't read it, but now I'm dying to. Graham, thank you so much for joining us again on Rationally Speaking. It's been quite a pleasure having you.
Me too, Julia.
This concludes another episode of Rationally Speaking. Join us next time for more explorations on the borderlands between reason and nonsense.
The Rationally Speaking podcast is presented by New York City Skeptics. For program notes, links, and to get involved in an online conversation about this and other episodes, please visit rationallyspeakingpodcast.org. This podcast is produced by Benny Pollack and recorded in the heart of Greenwich Village, New York. Our theme, Truth, by Todd Rundgren, is used by permission. Thank you for listening.